My name is Kim Gokoffski, and I'm an assistant professor in the Department of Ophthalmology at the University of Southern California, Roski Eye Institute. I'm a clinician scientist, which means that in addition to running a research lab, I'm also a physician. Specifically, I'm an ophthalmologist who specializes in neuro-ophthalmology. I'm not sure you've seen a neuro-ophthalmologist before, but we treat conditions that interrupt the communication between the eye and the brain. So this includes diseases that prevent the eye from transmitting visual information to the brain, leading to blindness, as well as conditions that prevent the brain from controlling the eye, leading to problems in coordination. Many of the conditions I treat result from damage to the optic nerve, which is the cable that connects the eye to the brain. Damage to the optic nerve leads to peripheral or central vision loss. The most common disease affecting the optic nerve is glaucoma, which is a neurodegenerative disease of the optic nerve. Patients lose peripheral vision slowly and can become legally blind, with many having to relinquish their driver's license. Aside from glaucoma, I also see patients who suffer from strokes of their optic nerve, traumatic damage to the optic nerve, such as experienced by servicemen in the military, or from compression from a brain tumor. The problem with damaging the optic nerve is that it has very little capacity to repair itself when damaged and no capacity to self-regenerate. What makes matters worse is that there are no treatments to restore vision to patients blinded by optic nerve diseases. In other words, vision loss from optic nerve disease is permanent. The annual economic burden in the US is estimated to be $139 billion, with numbers rapidly rising. Importantly, the impact of optic nerve diseases like glaucoma is inequitable. African Americans are 6 times more likely to develop and 15 times more likely to be blinded by glaucoma than Caucasians. Glaucoma also disproportionately affects women. What makes the burden of glaucoma tremendous is that most patients aren't even aware that they have the condition. In terms of traumatic damage, data from the Department of Defense shows that traumatic optic neuropathy accounts for $2.4 billion per year in treatment, benefits, and potential loss of productivity claims at the VA alone. The total lifetime cost for a single bilaterally blind soldier is estimated to be $79.5 million. Clearly, there is a pressing need for the development of therapies that can direct survival and regeneration of the neurons that make up the optic nerve. These neurons are called retinal ganglion cells. And so you might ask, what will it take to regenerate the optic nerve? Regenerating the optic nerve requires a multidisciplinary approach to overcome 4 major obstacles. Obstacle number 1, generating a source of healthy retinal ganglion cells to replace lost cells. If you asked us 10 years ago, the thought of being able to generate new neurons was science fiction. Remarkably, scientists have made tremendous progress in the field, allowing us to regenerate retinal ganglion cells from stem cells harvested from patients' skin. Obstacle number 2, getting these cells to integrate into the retina, which is the tissue that lies in the back of the eye. Unfortunately, we've learned that simply injecting healthy nerves into the middle of the eye isn't enough to get them to integrate into the retina. So many groups around the world are working on developing techniques to increase integration. Obstacle number 3, directing damaged or newly transplanted healthy retinal ganglion cells to sprout a new appendage called an axon that will grow out of the eye into the optic nerve all the way to the brain. In the human, this distance spans 5 centimeters, which is a remarkable distance. And this is the focus of my lab's research. So my lab has developed collaborations with electrical engineers to develop electric field application into a technology that can promote retinal ganglion cell survival and direct them to regrow their axon to regenerate the optic nerve. You might ask, what are electric fields? So electric fields are actually naturally generated by our body and have been shown to promote wound healing, especially of skin wounds. So when our skin is cut, an electric field is generated where the direction of the field is oriented from the normal tissue to the center of the wound. And skin cells are sensitive to this electric current and direct their migration along the current to the center of the wound. And as they grow in, they heal the wound. And so, along a similar line of thought, we hypothesized that electric fields can be exploited to direct axon growth of damaged retinal ganglion cells. And indeed, our work has generated promising preliminary evidence to suggest that electric fields can direct retinal ganglion cell regeneration after crush injury. Not only are we able to direct full-length regeneration all the way to the brain, but we also will demonstrate functional recovery, meaning that these cells actually work and can transmit visual information. Here's an example of some of the exciting data that we've been able to generate. What you're seeing here is a video of mouse retina grown in a petri dish. So what we did is we took mouse retina and put it in a petri dish and fed it with growth factors. The mouse retina was exposed to an electric field, which is oriented in the vertical plane in this video. What you see growing away from the edge of the retina is a retinal ganglion cell axon, the actual structure that is damaged in the diseases I mentioned earlier. And you can see that this axon is growing towards the negative electrode within our electric field. When we flip the polarity of the electric field by 180 degrees, remarkably, the axon makes a U-turn and redirects its growth to the new negative electrode. These findings show us that electric fields have a tremendous potential to direct regeneration of damaged retinal ganglion cells to appropriate targets in the brain to restore vision to patients blinded by optic nerve disease. If we can get all axons that are damaged to regenerate all the way to the brain, this will allow us to overcome the final and fourth obstacle to optic nerve regeneration, which is reestablishing connections between the optic nerve and the brain. So you now might ask, what will it take to generate these therapies? The answer, of course, is resources. Resources to the NIH and the DoD that will be used to support innovative, collaborative, and multidisciplinary research. When looking at the NIH funding adjusted for inflation, the purchasing power of the NIH peaked in fiscal year 2003, almost 20 years ago, and then declined fairly steadily for more than a decade until 2016. Despite this, the fiscal year funding for 2021 program level is still 3.3% below the peak that was seen in 2003. I urge you to invest in research, because investing in research means literally investing in a brighter future. Thank you so much for your attention.